Hey, welcome to The Explainer. Today we're diving into something amazing, the invisible shapes that secretly run our entire world. And we're going to start with a question you've probably had since you were a kid. You've wondered this, right? I mean, you shake up some salad dressing, look away for a few seconds, and bam, they've separated again. Why? What's going on there? What cosmic rule are they following? Well, it's not magic, it's chemistry. The secret is hiding in the tiny, three-dimensional shapes of molecules. So today, we're going to be detectives. We're going to go on a hunt and find that secret together. Okay, so to really get this, we have to start small. Like, really small. We're talking about the most important players in this entire game, the electrons. They're the ones who write all the rules for how atoms get together. And specifically, we're talking about a certain type of electron, the valence electrons. Now, these are the cool ones. They're the outermost electrons, the ones right on the edge. You can think of them as the social butterflies of the atom. They're the deal makers, the ones that decide literally every single chemical reaction. So how do we even keep track of these things? It's actually pretty simple. We use a handy little tool called a Lewis dot symbol. So for an element like oxygen, which has 6 of these super important valence electrons, we just draw its symbol, the O, and pop 6 little dots around it. That's it. This simple drawing is our map for understanding exactly how it's going to behave. All right, so picture this. Atoms are approaching each other. They're valence electrons at the ready, and they have to make a fundamental choice, a big one. Do they share their electrons with a neighbor, or do they just steal them? And that choice leads to the two main types of chemical bonds. On one side, you've got ionic bonds. That's the stealing route. It's all about a complete transfer, one atom giving an electron to another. And on the other side, you've got covalent bonds. This is the sharing option, where atoms agree to share electrons between them. A perfect example of an ionic bond? Good old table salt. You see, sodium has one valence electron it is dying to get rid of, and chlorine is desperate to get one more. So sodium just gives its electron over to chlorine. Now sodium is positively charged, chlorine is negatively charged, and as we know, opposites attract. Boom, you get sodium chloride. Okay, now for the sharing team. Let's look at water. Oxygen needs 2 more electrons to be happy, and each hydrogen atom has one it's willing to share. So they make a deal. They form these really strong covalent bonds where they all share their electrons. This sharing is what creates that incredibly stable, life-giving molecule we call water. And you gotta remember this one, because water, it's kind of the hero of our story today. All right, so we know how atoms connect. Now we get to play architect and learn how to actually draw the blueprints for these molecules. They're called Lewis structures. It sounds complicated, but trust me, it's just a 5-step process. First, count up all the valence electrons you have to play with. Second, figure out how to arrange the atoms. Third, connect everything with single bonds. Fourth, you hand out the rest of the electrons until every atom has a full set of 8. That's the octet. And finally, if you run out of electrons before everyone's happy, you start making double or triple bonds. Let's put this into practice. Let's build carbon dioxide, the stuff we breathe out. So, carbon has 4 valence electrons. Each of the 2 oxygens has 6, so 4 plus 6 plus 6 gives us a grand total of 16 electrons to work with. Easy. We'll put the carbon in the middle and stick the oxygens on either side. But, there's a problem. If we just use single bonds and fill in the dots, the carbon in the middle isn't satisfied. It doesn't have its full octet. So, what's the solution? They have to share more. The carbon forms a second bond with each oxygen. And now, with 2 double bonds, look at that. Everyone is stable. And that is the final Lewis structure for CO2. So we've got our 2D blueprints. But this is where our investigation takes a huge turn. Because molecules don't live on a flat piece of paper, do they? They live in our world, a 3D world. So take methane, CH4. When you draw its Lewis structure, it looks just like this, right? A simple, flat little cross with carbon in the middle, hydrogens all around. But come on, think about it for a second. Do you really believe that's how it exists in reality? That the building blocks of the entire universe are flat? Of course not. The 2D drawing is a lie. I mean, it's a useful lie for sure, but it's a lie nonetheless. So to get to the truth, we need something called VSEPR theory. Now, it sounds super complicated, but the core idea is incredibly simple. All those pairs of electrons in the bonds, they're all negatively charged. And what do negative charges do? They repel each other. They push each other away to get as much personal space as they possibly can. This one simple rule is the architect for everything, from simple molecules to the massive complex shapes of proteins and even the DNA in our cells. So, for our little methane molecule, those 4 electron pairs don't just settle for a flat 90-degree cross. No way. In 3 dimensions, they can get way farther apart. They push and they shove until they form this perfect little pyramid, a tetrahedron, with exactly 109.5 degrees between each bond. This is the molecule's true shape. Okay, let's take a breath. We have bonds, we have our 2D blueprints, and now we have the true 3D shapes. We finally have all the clues. It's time to solve the mystery of oil and water once and for all. The final piece of this puzzle is a concept called electronegativity. It's a fancy word, but it's a simple idea. It's just a measure of how much of an electron hog an atom is. An atom like oxygen, for instance, is an absolute bully. It pulls shared electrons really, really strongly towards itself. Hydrogen, on the other hand, is pretty chill. It has a much weaker pull. Now let's go back to our hero, the water molecule. Remember, its 3D shape is bent, right? It's not a straight line. Well, that greedy oxygen atom pulls the shared electrons away from the 2 hydrogens, making the oxygen end of the molecule slightly negative and the hydrogen end slightly positive. This makes water a polar molecule. It's like a tiny, tiny magnet with a positive pole and a negative pole. And in chemistry, there's one golden rule that explains almost everything about mixing. It's beautiful and simple. Like dissolves like. Polar things want to hang out with other polar things, and nonpolar things stick with other nonpolar things. So you get this whole army of tiny polar water magnets, and they love to surround and pull apart other polar things, like salts or sugar. But then oil comes along, and oil molecules, they're nonpolar. Their charges are all balanced out. So the water molecules basically look at the oil, and they're just not interested. They stick to each other, and in the process, they push all the nonpolar oil molecules together and out of the way. And just like that, mystery solved. It all comes down to shape and charge. It's that simple and that profound. So the next time you see soap making bubbles, or notice that smell right after it rains, or even just take a breath, ask yourself this: what other everyday phenomena are secretly being run by these invisible shapes that rule our world?